On any flat surface, what's the shortest distance between any 2 points? You would say the length of the straight line connecting the 2 points. This thing can actually be proved by using the concepts of calculus of variations. But is this always true? Let's take a sphere and do random points on it. What's the shortest distance between the 2 points if we are restricted to move only along the surface? Well, it's this curved line. Now it's no more a straight path. A common name which is assigned to the shortest paths between any 2 points on any surface is called a geodesic. David Hilbert had given a proposition which said that we should construct and study the geometries in which straight line segments are the shortest distance between any 2 points. This proposition is now known as Hilbert's fourth problem. It finds its importance from number theory to calculus of variations. In this video, we'll try to understand a few concepts and ideas associated with this problem. The theorem says, suppose we have two triangles on the same plane named as the following. Extend the lines AB and small ab, BC and small bc, AC and small ac. They are supposed to be collinear, lying on the axis of perspectivity if the extended lines A small a, B small b and C small c coincide at a point which we call the center of perspectivity. Metric space. It is basically a pair including a set and a function which maps in the following way. Now this function D has the following properties. In case the two elements x and y are distinct, D of x, y is always positive. The order of placing x and y does not matter here, and if the elements are the same, we get 0 on applying the function. And finally we have this particular inequality. The function is called metric or the distance function. Understanding these properties is very easy if we think about distance between any 2 points. Of course, if x and y are two distinct elements, the distance between them is always positive. The distance between x and y is same as the distance between y and x. The distance between an element and the element itself is obviously 0. And the final inequality is just the triangle inequality, which says that the sum of the lengths of two sides of a triangle is always less than the length of the third side. Now, why is this important here? Well, in order to solve the problem, we need a metric space which is disorganization. In other words, a space where the theorem and the converse hold true. An n-dimensional projective space is represented as the following. Taking an n plus 1 dimensional vector space, if we take all the lines passing through the origin, in other words, all the one-dimensional vector subspaces and make the collections, we get a projective space. George Himmel proved that every solution to Hilbert's fourth problem can be represented in a real projective space if we can determine the congruence of the line segments by equality of the lengths in a spatial metric, where the lines of the projective space are geodesics. We call this special matrix flat, and we just need to determine all the flat metrics. Herbert Buseman had introduced a new class of flat matrix where he introduced a measure sigma on the lines of the projective space Rp2, which follows the following conditions. For a set of lines passing through a point P, the measure yields 0. If the lines pass through a specific set containing a straight line segment, it is positive, and its value is finite for Rpn. Now, why is this important? Sigma metric on Rp2 is flat. In other words, geodesics are straight lines of the projective space. Now, this is what we have been looking for. Hilbert's fourth problem got completely resolved for the second dimension as Pogorelov proved the following theorem, which says that any two-dimensional continuous complete flat metric is a sigma metric in the year 1973. Another proof was made by Hilbert in 1976. For the third dimension, the work was a bit similar to the former one with some additional cases. The case of multidimensions was studied by Sabu and he proved the generalized form of Pogorelov's theorem. He defined all continuous flat metrics in terms of generalized functions. In spite of all the works, Hilbert's fourth problem is claimed to be too vague to be stated, resolved or not.